Hey everybody. So I'm at home here trying to get over some COVID symptoms that I started getting around Sunday evening. Thank you for your flexibility as you watch the documentary recently. We are at a transition point from one unit to the other, which has taken me a little longer to think about how to do this best for you. So I'd like to go ahead and try and do a lesson with you by video. And you could rewatch any of the pieces that you need and figure out how things go from there. So this would be our do now that would be in class. And the question is, you've got this person spinning a bucket around. Normally I would be doing this in class, which is much more interesting. But here we've got a guy, and he's spinning the bucket full of water on a string. Excuse me. And the question is to go ahead and draw a free body diagram for the water in the bucket at any point. So whether that be a point that is at the top or left or right or below, in that free body diagram, you definitely have one force that is always acting on everything, at least close to the surface of the earth, which is gravity. So gravity is always pulling down in each of these cases. But are there any other forces that are acting on the bucket and or the water that's in the bucket besides gravity? Well, that's what we're going to be talking about today. The part that is making it go around in circles. And that part is what creates something called uniform circular motion, as long as we have something that is traveling in a nice, even path all the way around. So that's my goal for you today. I provided some extra videos to be able to back things up. This is a video from Flippin' Physics where he demonstrates very nicely kind of what keeps the water in the bucket. And I highly encourage you to go back to our daily agenda to take a look at it, because it's quite good. And you can understand kind of what exactly are the forces and what keeps it in the bucket along the way. So feel free to go back to that video and take a look at it, but I'm not going to play it here, even though it looks like I am. Secondly, my goal for you when you're done with all this is for you to be able to list the conditions required for uniform circular motion, which are pretty straightforward. Be able to explain the acceleration of objects moving in a circle at a constant speed, and to be able to solve some problems involving calculations of centripetal acceleration. That's quite a word, centripetal acceleration. If you look down below, you'll notice that I've got quite a lengthy assignment that I'm calling problem set number 6 that you'll find in Google Classroom. That assignment is probably going to take you through Friday to be able to do all of them. They are some conceptual questions and some multiple choice questions, but in order to get through all of the kind of backup information to be able to get there, including this video, it'll probably take you a while. And so we'll go ahead and finish that assignment on Friday in order to make sure it makes sense. I might add a few extra problems in there for Friday, but probably not. We'll see. Sorry. All right, so I'm going to flip over to a PowerPoint, which you can get to via this link in the slide deck here if you want to. And I'll go ahead and start us off understanding what this is all about. So here we have it. We've got uniform circular motion. And let's talk about all the necessary pieces that make this work. So the part that makes uniform circular motion happen is that it requires a constant speed, right? So uniform means constant in this case. Secondly, is that it needs to be following a circular path. So as long as you have those two things, we get uniform circular motion. So is an object that's undergoing uniform circular motion accelerating? Well, let's think about what accelerating means. Accelerating means you're changing your velocity. You're changing how your motion is. And since velocity involves a magnitude and a direction, you are actually constantly changing direction. You're not going the same straight line path the whole way through, so you're always going kind of in a different direction. If you're going to think about the points of a compass, you're going north for a while, then east for a while, then west for a while, then south for a while, or however, north, then west, then south, then east. That would be better. So you're constantly changing direction, therefore you are constantly accelerating. So here I have an item or an object that is going around in a circle. Um, Due to the limitations of animations in PowerPoint, it doesn't look like it's going in uniform circular motion, but I'd like you to imagine that it is traveling at a constant speed around that circle for the purposes of this project. So it is going in a circle. We've got that, and we're imagining that it's always going at the same speed. So what is the actual kind of direction that this thing is going? Well, it depends on where it is. And remember, the way we talk about this is that we think about it in terms of straight line motion. So at any given point in the circle, you can think about its motion being in a straight line from that point. So here, right, as we were working our way around at any given point, those are the directions that it is traveling. Meaning that if I had some object and I had it on a string and I was whirling that object around in a circle, that those yellow lines would be the directions that it would leave when I let go of that string at that point. So just right over here, if I let go of the string at this point, the object would travel straight off, not in a circle or not in an arc away from things. So it always travels off. And the word that we use for this is tangential, coming from the tangent to the circle. So this is tangential velocity. Tangential velocity, straight line velocity, always perpendicular to the normal to the circle is what we've got. So what we can do with this is we can look at it and recognize that at any 2 points in the circle, it has different velocities. And with different velocities, we can recognize that we have some sort of acceleration. So let's take these 2 velocities for a moment and recognize we can come up with a change in velocity from them. So I've got here the velocity that's kind of up and to the right and the velocity that is straight up. Remember that when we find changes in velocity, we take the final velocity and we subtract the initial velocity from it, which means that I'm going to turn around the initial velocity and add it to the final velocity. So here's my final velocity. I'm going to turn around the initial velocity and I'm going to add it to it, which means that this is the direction of my change in velocity. That's my resultant for my vectors. Turns out that this direction, if I place it back on the circle, is pointing towards the center of the circle, which means the change in velocity vector is pointing straight toward the middle of the circle. And that's true for any of our changes in velocity, which means that our acceleration is always pointing towards the center of the circle, no matter where it is around. And that is called circular acceleration, also known as centripetal acceleration. Centripetal acceleration is a fancy word that means center seeking. Center seeking. So centripetal acceleration, center seeking acceleration is the one that causes things to travel around in circles. And the way we can calculate that acceleration is here with a v squared over r. Now, to get this v squared over r takes a little bit of calculus to get there. So I'm going to skip over the calculus for the moment, and I'm just going to point to this factor and say, okay, now that we have this idea, this v, which we call the tangential velocity, if we were to square that velocity and divide it by the radius itself of this circular path, that's what is going to give our acceleration as a whole. So the greater the velocity is that's tangential, the greater the acceleration. Also, the smaller the radius is, the greater the acceleration. Interesting. So if a car is accelerating, is its speed changing? Well, not necessarily. Remember that speed does not involve direction. And so if a car is accelerating, it might just be traveling around a path or a curve. And that speed might stay exactly the same the whole time, or it might be traveling at 20 miles per hour all the way around the curve. But because its direction is changing, it's accelerating. How about this? In the diagram below, a cart travels clockwise, right? So clockwise, at a constant speed in a horizontal circle. At the position shown in the diagram, which arrow indicates the direction of the centripetal acceleration of the cart? What we learned just a moment ago is the direction of the acceleration as we go around a circle is always towards the center, which is centripetal acceleration or center seeking. So A would be your direction for your centripetal acceleration. Secondly, which arrow indicates the direction of the tangential velocity? Well, if it's going around in a circle here, the tangential velocity is the one that is tangent to the circle, which is this one, C, going in a straight line. So there we have it. A is your acceleration, C is your tangential velocity. The diagram here shows the top view of a 65 kilogram student at a point A on an amusement park ride. This happens to be one of my favorite amusement park rides of all time. Growing up, we called it the rotor, but there's a number of different names for it. It's a ride that spins around in circles super fast, and then at a certain point, the floor drops out from it, and the people stay positioned on the wall. So the ride spins, and the student on the horizontal circle of radius 2.5 meters at a constant speed of 8.6 meters per second. The floor is lowered, and the student remains against the wall without falling to the floor. The question here, and we'll analyze this ride a little more later, is which vector best represents the direction of the centripetal acceleration of the student at point A? So if the student is down here at point A, we need the vector that is pointing towards the center of the circle, which means that of these four vectors, the only vector that's pointing towards the center of the circle would be vector number 1. So that would be the centripetal acceleration for that student. Sorry, these pictures are a little bit blurry, but I had to lift them out of a text to be able to get this. So which graph best represents the relationship between the magnitude of the centripetal acceleration and the speed of the object moving in a circle of constant radius? Well, if you remember, the centripetal acceleration is equal to v squared over r. So if we're looking at the comparison between A and V, if you have v squared, we need a graph that is squared in nature. So it is not linear, and it doesn't drop, and it's not constant. The only one that works here is that as the speed increases, the acceleration goes up as the square of that velocity. So we have an exponential graph here, which is B is the answer. All right, a couple more questions here to get us going. If I have a 0.5 kilograms object, that moves in a horizontal circular path with a radius of 0.25 meters at a constant speed of 4 meters per second, what is the magnitude of the object's acceleration? So 0.5 kilogram object moving in a horizontal circular path with a radius of 0.25 meters at a constant speed of 4 meters per second. What's the magnitude of the object's acceleration? Well, if we know that the object's acceleration is v squared over r, does the mass matter for the acceleration? And the answer is no. So in that particular case, we can just take the speed, which is 4 meters per second, and we can square that to get 16, and then we're going to divide that amount by the radius, which is 0.25. And if we take 4 squared divided by 0.25, we get an acceleration of 64 meters per second, which is quite high. 64 meters per second is a decent amount of acceleration, but not unreasonable. So 64, and then notice that I did not need the mass on that one. All right, we're almost there. An important note is that centripetal force is not a special kind of force in and of itself, right? This center-seeking force. Rather, it's provided by other forces, such as gravity, such as the moon going around the Earth. The centripetal force for the moon is provided by gravity, or tension in the sense of a string tied on an object, getting it to go around, or friction, as in like a car traveling around a curve. So again, centripetal force is just a label that we placed on an existing force when it's directed toward the center of a circle. So you can have a frictional force that is a centripetal force, or gravitation that is a centripetal force, or tension that is a centripetal force, but it is not some new kind of force. I chose to scrap an puzzle. If you ran into this yesterday, please ignore it. But I did place a couple crash course videos that I would like you to watch. Originally, I had an ed puzzle scheduled with one of them, but I think it's going to be more beneficial for you just to go ahead and watch them to get some vocabulary and terminology down. And so ignore it if you spotted the ed puzzle yesterday. We're not going to do an ed puzzle on these two things, but I'm going to point out that I have a couple videos in Google Classroom connected to this assignment. All right, so here's our big equations. One of them we've seen so far, which is this centripetal acceleration here, which is v squared over r. But it's not that far off to look at Newton's second law. Newton's second law is F equals ma. So if you know that you have an acceleration, if you multiply that acceleration times a mass, you get a force. So the centripetal force, the force that's causing it to go around in a circle that could be gravitational, or it could be frictional, or it could be tension, is just found by taking the acceleration, which is v squared over r, and multiplying by the mass of the object itself. And that gets to your centripetal force causing things to go around in circles. That will be useful quite a lot as we try and understand how to solve some problems dealing with this. So let's take a problem and see if we can figure it out. I have a problem here that is dealing with a car traveling around a corner. But in this case, the force that is centripetal is being provided by friction. So on a snowy day, when the coefficient of friction, static friction, so this is rolling friction, between a car's tires and the road is 0.5, the maximum speed that the car can go around the curve is 20 miles per hour. What is the maximum speed at which the car can take the same curve on a sunny day when the coefficient of friction is 1? So again, here's the things to know. Coefficient of friction on the snowy day is 0.5, on the sunny day is 1, and the maximum speed that we can go around is 120. I've got some choices here to choose from, but I'm going to actually flip across to a different program here to be able to help me draw some things down. And this is a whiteboard that I can draw on here, and I'll do my best to make sense of this. So I've got this car that's traveling around a corner. Oops, let me grab my right pen. Car that's traveling around a corner, and its maximum speed that it can go around the corner is 20 miles per hour. And it can do this in a snowy day when the coefficient of friction, static friction, right, is 0.5. And on a dry day, it can do it with a coefficient, this is for the snow. And on the dry day, the static friction is 1.0 for the dry. How in the world do we solve this problem? Well, let's break it down into the two pieces that we've got. First, let's look back at our friction equation. The force of friction, we know, is equal to the coefficient of friction times the normal force. And in the case of a car traveling around a corner, the normal force is going to be given just by the weight of the car. So that means that the force of friction here is equal to the coefficient of friction times the weight of the car, and I'm going to write that in here as mg. Now this force that we're talking about is causing the thing to go around in a circle. So if it's going to go around that curve, kind of a circular curve there, then we can say that we have a force that is centripetal here. And we know that that's equal to the mass of the car itself times the velocity of that car squared over the radius of that curve. Now we can say, well, this centripetal force is really just being provided by the force of friction. So I can set these two things equal to each other. And you'll notice that as I do that, I've got my coefficient of friction times the mass times the acceleration due to gravity is equal to the mass of my car times the velocity squared over the radius. As is often the case, my masses cancel out, and I don't have to worry about them anymore. And so I have the coefficient of friction times the acceleration due to gravity is equal to v squared over r. I might as well solve this for velocity because that's what I'm trying to get in the end, is I want to know kind of how fast the car can go around the curve when it is not snowy, because when it is snowy, it's 20, and I want to know how fast it can go around when it is dry. So if I solve this for v, I get v is equal to mu g r, and I need to take the square root of it. So that's what my velocity is in any case as I go around. So let's break this down into two parts then, making sure that we understand what those two parts are. I'm going to do one where it is snowy and one where it's dry, right? Because the velocity when it is snowy is equal to the square root of mu times g times r. And the velocity when it is dry is equal to the square root of mu times g times r, where the only thing that's different here is this coefficient of friction, where this is really the coefficient of friction for a snowy climate, and this is the one for the dry. If I was to set this up in a ratio of these two things, where snowy is on top and dry, got my v, and the velocity of dry is on the bottom, I'm going to do that here with the square root of mu s g r, that's for snowy, and the square root of mu d g r for dry. And if I recognize this, I have a square root of gr and a square root of gr on the bottom here. Turns out that I can actually cancel these two things out, which means that I can actually get this as just a ratio of the two coefficients. So I have, oops, too many extras. I've got the coefficient for snowy divided by the coefficient for dry, because this part will cancel out. It's on the top and the bottom, so I don't have to worry about those two either. So to figure out what the dry is, I just essentially need to rearrange a little bit. What's the best way to do that? Well, if I want to solve for dry, I suppose I want to multiply by snowy and flip. So really I could flip these two over, and I could flip the other two over as well. And then I could solve it a little bit more easily. So I'll do that, where I've got Vd over Vs is equal to the square root of the coefficient of dry divided by the coefficient of snowy. Sorry for the change. But if I multiply now by snowy on both sides, it's going to cancel over here, and I'll get my velocity dry on this side, and that's my snowy. So I'll go ahead and do that just now because I know all of my pieces, and I've got the velocity of my dry is equal to the square root of dry, so this is 1, divided by 0.5, right, times 20 miles per hour. And 1 divided by 0.5 is 2, so this is the square root of 2 times 20. And so I'll go ahead and do that right now. So the square root of 2 times 20 gives me 28 miles per hour. Sounds pretty good to me. So my final answer to this question is a whopping 28 miles per hour. Now, there's lots of different ways to solve this. I could have solved for the radius of curvature, and then I could have done a little fancy footwork there, but this is not a bad problem. I'm going to leave this here for the moment. And I have a couple other problems to solve, but I'm going to leave them for Friday. That's enough to get you started on what you need. So for now, know that we've got a good chunk of information that can get you started on this assignment itself. I want to point out a couple things right in Google Classroom to help you get there. I put these two crash course videos that are in here. One's 9 minutes and one's 8 minutes. The purple one is a little bit more basic and goes through the things that I went through right now. And if you're getting to the end of the assignment and you're working on some things and they're dealing with some rotational stuff, feel free to watch this one. But I will go ahead and make a further video on this to help us out for Friday. So we're going to finish this work on Friday. These are if you need to work ahead, but these are the assignment and the problems. So good luck, and I will get back to you on Monday when I finally am past quarantine. I'm doing okay, but clearly I'm not perfect yet. So love you guys. Take care. Bye-bye.